Hello dear students, welcome to my channel Conceptual Physical Chemistry. Myself Dr. Shariyu Thorat, Associate Professor of Shivaji College of Arts, Commerce and Science, Akola. In this session we are going to discuss the important part of photochemistry, that is the derivation of Lambert-Beer's law, which is an important law governing absorption of light. What is Lambert's law? In the year 1758, J.H. Lambert derived a relationship between the amount of light absorbed and the thickness or depth of the absorbing material. According to this law, when a beam of monochromatic light passes through a homogeneous absorbing medium, the rate of decrease of the intensity of radiation with the thickness of the absorbing medium is proportional to the intensity of the incident radiation. As you can see in the diagram, we have shown a source of light and a filter. I0 is the intensity of the incident radiation. This incident radiation passes through the sample and the light which is transmitted is shown by the letter I. Mathematically, this law can be written as minus di by dx is proportional to the intensity of the light I. Now if you remove the proportionality sign, the equation becomes minus di by dx is equal to k into I, where k is a constant which is called absorption coefficient. X is the thickness of the medium and I is the intensity of the incident light. On rearranging equation 1, we get minus di by I is equal to k into dx, which is equation 2. Now if you integrate equation 2 between the limits, initial limits, I is equal to I0 at x is equal to 0 and I is equal to I at x is equal to x. So if you integrate equation 2, we get integral I0 to I di upon I is equal to minus k into integral x is equal to 0 to x is equal to x of dx, that is equation 3. If you solve this integral, the solution is log I upon I0 is equal to minus k into x, equation 4. Now if you remove the log from equation 4, it becomes I upon I0 is equal to e raised to the power minus k into x. The equation can also be written as I is equal to I0 into e raised to the power minus k into x, which is equation 5. Now in the next step, we are going to write equation 4 by removing the log and writing as log to the base 10. Now according to equation 5, the intensity of beam of monochromatic radiation decreases exponentially with the increase in the thickness x of the absorbing substance. Now equation 4 can be written as, now here you are writing log to the base 10. So you have to multiply it by 2.303. Then ln becomes log, that is log of I upon I0 is equal to minus k into x, equation 6. It can be written as log of I upon I0 is equal to minus k divided by 2.303 into x. Or it can be written as log of I upon I0 is equal to minus epsilon into x, equation 8. The equation can be written as log of I0 by I is equal to plus epsilon into x. Now what is this epsilon? It is called as extinction coefficient, which depends upon the nature of the absorbing substance and the wavelength of incident light. Now what is Beer's law? Beer in the year 1852 extended the Lamberts Law to solution. Now according to this law, when a beam of monochromatic light passes through a solution of an absorbing substance, the rate of decrease of intensity of light with the thickness of the solution is proportional to the intensity of the incident light as well as concentration of the solution. So Beer's law is applicable to the solution. So the law can be written mathematically as minus di by dx is directly proportional to the intensity of the incident light as well as the concentration, that is C, of the solution. So minus di upon dx is equal to epsilon alpha into I into C. Now what is this I? I is the intensity of the incident light, X is the thickness of the medium, and alpha is the constant called absorption coefficient. On rearranging equation 1, we get di upon I is equal to minus alpha into C into dx. Now as we have done the derivation in case of Lambert's law, here also we have to integrate equation 2 between the limits I is equal to I0 at x is equal to 0 and I is equal to I at x is equal to x. So when we integrate equation 2, integral I0 to I di upon I is equal to minus alpha into C into integral dx. The limit is x is equal to 0 to x is equal to x. That is equation 3. Now equation 3, if you solve the limits, the answer is log of I upon I0 is equal to minus alpha into C into x. That is equation 4. Equation 4 can be written in the form of exponential form if you remove log. So I upon I0 is equal to e raised to the power minus alpha into C into x. Or it can be written as I is equal to I0 into e raised to the power minus alpha into C into x. So what does equation 6 signify? According to equation 6, the intensity of the beam of monochromatic radiation decreases exponentially with the increase in the thickness x and the concentration C of the absorbing substance. Equation 4 can be written as 2.303 into log of I upon I0 is equal to minus alpha into C into x, or it can be written as log of I upon I0 is equal to minus alpha divided by 2.303 into C into x, or it can be arranged as log of I0 by I is equal to plus alpha divided by 2.303 into C into x. So we get the mathematical form of Lambert-Beer's law in the form of equation 10, that is log of I0 by I is equal to epsilon into C into x. Now what is epsilon here? Epsilon is called molar absorption coefficient, or it is also called as molar extinction coefficient or molar absorptivity. It is the characteristic of the solute which depends upon the nature of the solvent, temperature and wavelength of the incident light. Now if you express the concentration is in molar per decimeter cube and the path length x in centimeter, then epsilon, the unit becomes decimeter cube per mole per centimeter, and it is referred to as the molar absorption coefficient or molar extinction coefficient. The quantity log of I0 by I, it is also called as optical density or absorbance of the medium, denoted by A. That means you can write the left hand side of Lambert-Beer's law, that is log of I0 by I, that is equal to A, that is equal to right hand side epsilon into C into x. Or you can calculate the value of epsilon as A divided by C into x. Now the unit becomes liters per mole per centimeter. Now if the concentration is expressed in 1 moles per liter, x is equal to 1 centimeter, then molar extinction coefficient epsilon is equal to A. The transmittance T is given by the formula T is equal to I divided by I0, or if you express in percent transmittance, then it is equal to I upon I0 multiplied by 100, where I is the light transmitted through the sample and I0 is the incident light, that is light directed into the sample. Absorbance and transmittance are also related as A is equal to 2 minus log of percent transmittance. Now Beer's law is applicable to dilute solutions only. Now let us discuss the definition of epsilon. Molar absorption coefficient or molar extinction coefficient or molar absorptivity, that is epsilon, is defined as the absorbance for a concentration of 1 mole per liter of the absorbing substance and the optical length of 1 centimeter. So this is the definition of epsilon. Now let us discuss the limitations of Beer's law. The law shows deviation due to the following facts. If the solution is highly concentrated, deviation may occur if monochromatic light is not used. Deviation may occur if solution is turbid or contains air bubbles. Deviation may occur if some experimental condition, that is pH, temperature, ionic strength, etc. is not maintained. Now applications of Lambert-Beer's law. This Lambert-Beer's law is used to determine the unknown concentration of a compound by comparing with a solution of known concentration using a spectrophotometer. It is also used to characterize a compound by drawing the absorption spectrum and to measure the absorbance of a compound by using spectrophotometer. That's all for today. Have a wonderful day.